as you can see here, today I'm just going to go over a bit of beam theory. It's the very basics. It's simply supported beams with point loads. Anyway, typically, well, I've already detailed out the start of this question. This is what you'll come across. This is a free body diagram of a simply supported beam, i.e. it abides by the rules of being statically determinate, which simply means the main rules for it are that two joints, well, two supports, support A, support B, beam, and there's three reaction forces, i.e. horizontal force, vertical, and a vertical. Well, I'll just write it out again because it makes it easier to picture. You'd start out with a beam like this, and they'd have drawn on a roller support and a pin support, 2 points. Reason it's on a roller, like I say, you have to have three reactions for it to be statically determinate, which means you can determine the assumptions that we make, which I'll get into in a minute. Static, i.e. it's not moving, which is good. That's what we want. This is structural engineering. Things don't move. So the three reactions, you can work out if it's two supports, it's going to have a vertical support, and due to this rolling support, that means it's allowed to move if it wants to. It can move by this much or whatever, which means there's no horizontal restraint. There's nothing holding it there, which means there's no horizontal reaction force. Here though, it's fixed. It's a fixed support, which means there will be a reaction force stopping it from moving. It makes it very stiff. Reaction force pointing either that way or that way. It really doesn't matter. And that's what we've come to here. This particular question, I've labelled it with 12 kilonewton point load acting at these dimensions and a 17 kilonewton point load acting there. We're not going to get into UDLs just yet, which I'll talk about in another video. But basically, how we start this off after we've labelled everything, free body diagram labelled completely, reaction force B, reaction force A, horizontal from the fixed point. First thing that we do, which I got showed a couple of years ago, best way of starting out, just list your assumptions, your static assumptions, which is the sum of the forces in the x direction equal 0, and the sum of the forces in the y direction equals 0, and the sum of the moments equals 0. I can even write that as fx, fy, and f moments. Probably don't have to put the f there. These assumptions will help you out tremendously, because there'll be so many scenarios through the breakdown of very complex beams with multiple. It could be a fixed on one side. What's the word? Basically, you'd have one support, so a fixed end, and you could have a UDL, and it could be split with a node, a joint, midspan, all these other things. But as long as you have these, that basically means you can set out formulas and they're always equal to 0, which allows you to derive an answer. This is just a convention, a sign convention, which is very important. You always want to draw this out, because what I've done here is during axis y, x, and I said if it's If the arrow is pointing this way, positive. If the arrow is pointing this way, positive. Consequently, this is negative and this is negative, if you can see that. And then a moment arrow, rotation in this direction, which is clockwise, is positive. Consequently, if it's going the other way, negative. All this means is when you come to write out the formulas, due to the way we symbolise forces, we typically use arrows, i.e. this arrow is pointing down, this arrow is pointing up. That could be pointing down, it just depends on how you want to draw it. It really makes no difference. You just get a minus number if that answer is positive. You know, there is no right answer for which direction the arrows are pointing. I could draw that going up. It'd just be minus 12 kilonewtons if I did that. No difference, but as long as I have a sign convention saying that universally that's positive, that's positive, that's negative, and the same with moments. If that's pointing down, then that means that that is a negative force that we will write into the equation, and that will be a positive force because it's facing up. That takes us on to our next bit. Just going to draw a line and draw that. We'll start in this little bit here. First thing that we want to do with this to tackle it, now we've made all the assumptions, is taking moments from a point. We've got point A and point B, it's a very simple beam. So I'm going to go straight ahead and say we're taking moments at point A, which we write as sum of moments A equal, and from here, depending on how familiar you are with this, it's probably rather easy if you've done previous like A-level maths with moments and such. I'm going to assume nobody has a grasp of moments, so I'm just going to break it down as basic as it comes. A moment force, it sounds quite scary. All it is a rotation force. It's what's happening when I do this. I grab it at a point, that's the pivot, and I have a force acting at a distance, i.e. this distance to there, the point of the pivot to the end where the force is being applied, and I poke it that way. I apply a force that's perpendicular to the direction that is coming from the pivot. And that's how all rotation in physics and the real world work in anything. It's just someone holding a point where it's free to move and applying a force, and it makes it rotate. That's what a moment is. This is what it is. Made a point, and if I apply a force here, no moment because there's no distance from it. That will just point in that direction. There's not going to be any rotation, as you can just tell by knowing about life in general. If I've got a distance and then I apply a force there, well, you already know what's going to happen. That's going to rotate, and the amount of moment acting on that, the value for the moment, is going to be whatever distance that is times by the force acting on it. That is what a moment is. Moment force equals simply force times distance. There's the fundamentals of a moment. And that takes us onto this part. Taking moments at A, that means this node, this rotation, is now this point. And anything acting on it to make it rotate past this point is our moments. So what do we have? As reaction force there, that's not going to cause a moment because it's acting through it, there's no lever arm. Because both these arrows, even though I've drawn them there, are actually acting at this point. They're acting at the point that we're talking about. The same with this, it's acting through it, there's no lever angle, and all the lever arm, And also, due to no other horizontal force, sum of forces in the x direction equals 0. So we already know RAX equals 0. We can forget about that. It's irrelevant. That's why I don't usually add them in, but for the sake of fundamentals, this is how we do it. Next stage. This is a moment, this is a moment, and this is a moment, because they're acting at a distance and a force. This, due to it acting at that distance and it's facing downwards, would rotate this way. I hope you can see that. Consequently, same, this is facing downwards, it's going to go the same direction. But if you can predict this one, the arrow is going either way, so it would be going this way, wouldn't it? It'd be rotating that way, rotating that way, rotating that way. So these are our moments. So the first one, let's take the first one. Let's refer to our symbols, and that is a clockwise force, meaning that it's positive, and that's 12 kilonewtons, a distance of 4, so we times that by 4. Simple. Now I've put that as 12 and I've put that as 4. You cannot, that means I've made the assumption that all of these in the formula are going to be in meters and in kilonewtons. Do not change the units halfway through the formula. You will run into terrible trouble if you do that. Just in general, not with simple problems like this, it's probably not going to happen. But as they get more complicated, you're going to fuck up so easy. If I suddenly change that to newtons and I put it in as newtons, I'm going to be off by 1,000 units. So you're going to get the wrong answer. Same if I put it in kilograms, that's really going to fuck things up, because it's not only going to be off by 1,000, but it's going to be off by 9.81 times 1,000. So, you know, that's a hell of a lot. Okay, next one. That's also going in the clockwise direction, so it's positive. We put that in as a plus. Plus 17 kilonewtons times by, not 2, there's 2 there, don't make a mistake, I've done it before, there's 2 plus 4 because it's acting away from this point here, that one. 4 plus 2, 6 meters. Next, last one is acting in anti-clockwise direction, so consequently that is negative force, negative moment even. We'll write that as RB, so it's right, and that's acting at a distance of what? 2 plus 2 plus 4, it's acting at 8 meters. If we refer to the assumption, which is what makes all the magic happen, sum of the moments equals 0. So all of this, for it to be statically determinate, equals 0. There. Now that allows us to work it out. We just work it all through. I'm a lazy bastard. I can't really be fucked to work out basic maths. So 12 times 4, 48. This is how I've gone through my degree, literally. I don't even use my brain anymore. Whoever invented the calculator, I want to give him a pat on the back, to be honest. And minus RB times 8 equals 0. Now, I'm not sure what point everybody's at, but you should know by now with these formulas. If you want to find an unknown, you swap it onto the other side of the equal sign. And if you do that, if you want to change the side of the equal sign, you change the sign, i.e. negative or positive. Change side, change sign. God, I'm getting caught mouth now. So, first add these together, that comes to 150. And then we'll change the side that it's on. And it's on this side now, so we change the sign. It's now plus RB times 8. The next step is what you should know by now as well. If you want to get rid of this 8, which we do to find out RB, if you want to isolate it, you have to divide both sides by 8. But you should just not even have to write that in, you should just know by now. Because what happens is when you divide both sides by 8, these cancel out, leaving you with nothing times that. It's just 1. It'd be RB times 1, so RB on itself, and leaving you with 150 divided by 8. So the end product of that is 150 divided by 8 equals RB. I don't know. So what is RB? 150 divided by 8. 18.75. Therefore, that's what those dots stand for. RB, the unknown, reaction force of B equals 18.75. What does it? What are the units now? Let's see if we can work this out. Kilonewtons, meters, kilonewtons, meters, kilonewtons, meters. All these moments end up in kilonewton meters because they're times together. So that's 48 kilonewton meters, 102 kilonewton meters, and RB times 8 kilonewton meters. That is in kilonewton meters, and that is meters. So when you divide kilonewton meters by meters, meters cancel out. You're just left with kilonewtons. If you can't understand what units you're left with at the end of a formula, a big long equation that you've worked out, that's the best way of doing it. Just write the units in from start to finish and just cancel them out as they come. They work the same as numbers. I know because they're letters you might not think they do, but it works by the same laws. That's just the way it is. So consequently we're left with kilonewtons. 18.75 kilonewtons, our first unknown. But there's only 2 unknowns because we know that's 0, we don't need to find that out. So now it becomes even easier because what did I say at the start? Sum of forces in the y direction all equals 0. They must do. That's the laws and the assumptions that we stated. Consequently then, what we're going to do is put that into here. Sum of forces in the y direction equals 0. So consequently, if we put all of these in, forces in the y direction, that's facing upwards, going to be positive. RA facing down, negative, minus 12, minus 17, positive RB, which we now know as 18.75 equals 0, the lot of it. So now we're going to do the same thing. We're going to work these all through first, make it more simple. So, oh fuck me, I'm so lazy, Jesus Christ. Minus 12, minus 17, plus 18.75. That gives you minus 10.25. And that equals 0. So you can already guess what I'm going to do. If I want to change the side that it's on, to leave this on this side isolated, I change the sign. Reaction force at A equals then positive 10.25. RA equals 10.25 kilonewtons, because these are all kilonewtons, no unit change there. And there you go, your 2 reaction forces. And that is how you work out an easy, simply supported beam. This is the most fundamental way of working out you can possibly do. That's the start on the journey into mechanics of beams. Such. Alright, I hope you learned something. Signing out.